All right, so in this lecture, we're going to move into chapter 3 of Grossman, which is polar reactions under acidic conditions. So let's start by thinking about what the acids would be in this case. So the acids could certainly be the various types of acids that we typically see, that is Lewis acids or Bronsted acids, but you're probably more interested in what sort of specific reagents we could use for these transformations. So the Lewis acids would be AlCl3, FeBr3. We've seen these things in Friedel-Crafts acylation and alkylation reactions, and the Bronsted acids could be our typical strong mineral acids like H2SO4. Whoops. But this is an acid that comes with some water, and for a lot of the advanced organic transformations we want to do, we want to have an acid that's just as strong, but in the absence of water, or doesn't bring too much water around with it. We're going to rely on the triflate group, or the triflyl group again, to make triflic acid. So TFOH is triflic acid, and this has the structure CF3 SO3H, where the H at the end, the only H is our acidic H atom. Okay, so we have these various acids, whether they be Lewis or Bronsted, and there could be, I suppose, a few others too, but for the most part, these are the some of the bigger players. Let's talk about what types of reactions that we can do when we've got acidic conditions present. So let's get down here and we'll just emphasize this right away. Acidic conditions encourage the formation of carbocations. Okay, now when we look at these types of reactions, we have to first remember that the acid reacts first. So the acid reacts first and then forms, after it reacts, then it forms a carbocation. Now, once that carbocation is formed, we should remember some general rules about the stability of cations, carbocations in particular. As that will lead us to understand better why certain reactions happen the way they do. Now, in general, what we have to remember is that for carbocations, we want things that are more stable or more substituted. Of course, we want things that are more stable. So we want more substituted carbocations because they're more stable. And what this is referring to is that if you've got a carbocation on methyl, then you probably don't know your mechanism correctly. That's far less stable than a primary carbocation, which is even far less stable as a secondary carbocation. And then the most stable of all, I don't know if that's a double less than sign, is the carbocation with 3 groups attached to it. So the first one is methyl. It has 0 substituents replacing hydrogens. The second one, the carbon with the positive charge, has 1 substituent replacing a hydrogen, so it's primary. And then 2 substituents gives us secondary. 3 substituents gets us tertiary. And we have across the bottom here, we have increasing stability. Okay, so more substituted is more stable, tertiary is the most stable. Secondary has some mediocre stability, primary and methyl, excuse me, goodness, are just not that stable. So we could ask why. Why are more substituted carbons more stable? And that has to do with an effect called hyperconjugation. So again, that term is hyperconjugation. Okay, so hyperconjugation. So what's this? What we have with hyperconjugation is that we say that the non-hybridized p orbital is parallel to neighboring sigma bonds and is stabilized. So it's really stabilized by the parallel neighboring sigma bonds. Now, pictures are going to be much more valuable than words, so I'll get right into it. So let's say we have a carbon with a positive charge. I want to show that positive charge is existing somewhere, so I'm going to put it in an unhybridized p orbital. Then we have some groups that form the other three things attached to that carbon. It's planar, it's sp2 hybridized. The positive charge sort of exists in the non-hybridized p orbital, but in reality, it's just a non-hybridized p orbital. It doesn't have electrons, so it's not like a positive charge is existing. Positive charge is the absence of things. Now, what I'm saying is let's take a pair of electrons and put them in a sigma bond next door to that carbocation vacant p orbital. These two things, the bond with the two electrons and that vacant p orbital, are parallel to each other. So the negative charge of the sigma bond that's neighboring that non-hybridized p orbital is parallel, and what it's able to do is provide a very subtle, super weak stabilizing interaction to sort of dissipate its electron cloud. It's like its electron cloud reaches over and tells the vacant p orbital, hey, everything's all right. You may not have electrons, but I have electrons. And that's enough for that positive charge to be stabilized, much more so than if it were on, let's say, a carbon with three hydrogens, where there is not the opportunity to form a neighboring sigma bond. Now note, it's not the sigma bond connecting the carbon to things. That's not this sigma bond. It's the sigma bond next door to the carbon with the positive charge. And so in this case, if we had CH3s everywhere, as is the case for the tert-butyl carbocation, we could have the opportunity for either up or down parallel overlap with that p orbital of neighboring electron clouds that provides a stabilizing interaction on the positive charge, making it more likely to exist than it would if it didn't have those neighboring sigma bonds. Now, if we look at what this looks like with a methyl group, a CH3, all we have is the sigma bond reaching out to the hydrogen, and this does not stabilize through hyperconjugation. Now, if we wonder why it's conjugation. Okay. If we wonder why it's called this, conjugation means the ability for electrons to sort of dissipate across a large number of atoms within a molecule. So we saw conjugation with benzene. The 6 electrons can exist across all 6 of the elements in the pi system. Now here, the electrons don't really exist, so there's not really conjugation. It's just an electron cloud is felt and dissipates across the neighboring or dissipates a little bit closer to the neighboring carbocation to provide some stability. So it's not full-blown conjugation. It's kind of reaching and overextending itself, so we call it hyperconjugation. Okay, so we see hyperconjugation, but what about conjugation itself? So it turns out that conjugation actually beats hyperconjugation. Hyperconjugation is not a real conjugation. Now, another term for conjugation is resonance. That is to say, when we have conjugated molecules, we can draw a lot of resonance structures. Conjugation. Gosh, I can't get this word right while I talk. So when I say resonance, I'm referring to also conjugation. It actually beats hyperconjugation and provides a stronger stabilizing force. Okay, so if we take something like, here's our carbon with our vacant p orbital, and it's got stuff here and here. Now what I'm going to do is, instead of having a tert-butyl group, I'm going to have an allyl group present. Now that allyl group provides stability through resonance. Remember, we said in organic 1 that if you have resonance structures, you have increased stability. Now, when we do that, we actually dissipate the positive charge over to a CH3. So now this is sort of primary, whereas we started with tertiary. So maybe this over here on the left is a better contributor. I'm not going to argue with that. The one on the left is a better contributor to the carbocation structure, but labeling tertiary and primary doesn't apply here. This is just the same carbocation, and instead we would call it allyl. Allyl means next to a CC double bond. Okay, so we can put the positive charge, we can dissipate it across 3 atoms now. Now that's better. The positive charge is delocalized. And again, more resonance means more stability, because you're not locking the electrons to exist between only 2 atoms if they're shared. You're able to dissipate those electrons across several atoms, thereby enhancing the overall stability of the molecule. Okay, and we could look at this from a pi orbital, an orbital perspective. If we've got our vacant p orbital here, then we go to our alkene. Our alkene is just the overlap of neighboring p orbitals through a side-to-side fashion. So we have 2 electrons dissipated across 3 atoms in an allyl network. But the difference between these 2 electrons and the 2 electrons that we saw previously is these electrons can actually jump over to the positively charged atom, whereas before they couldn't. They could only their presence could only be minorly felt. Okay, so now what we're going to do is consider what happens if we've got these things, positive charges on pi systems that have, or in conjugation with heteroatoms. So it turns out that atoms with that are next to the positive charge that are both, let's say it this way, both next to the positive charge and have lone pairs, provide additional, provide stability. Not going to worry about comparing these. So provide stability, and I'll write to cations. Okay. Let's look at examples. Again, words can only go so far. If I have a positive charge at this position, and on this position I put an oxygen, that oxygen is just attached to something. Note that the oxygen has 2 lone pairs. They could come down and make a carbon-oxygen double bond in this case. The positive charge is now at the oxygen atom. This is actually a better structure. What's happened is the vacant p orbital that tells us we have a positive charge is parallel to one of the lone pairs, and that lone pair can just kind of come down and donate its electrons over, share them with that vacant p orbital through a side-to-side interaction, which we call a pi bond. Now, oxygen's a bit electronegative. If you introduce a less electronegative element like nitrogen, you get to even more stability because the lone pair is more likely to be shared between the carbon and the nitrogen, because the nitrogen, again, is less electronegative than oxygen. And just like before, the better contributing resonance structure is one in which everything has an octet, even though the more electronegative atom has the positive charge. It's not about the charge position when our structures have different electron counts at every atom. Okay, so these are examples of some of the most kind of stabilizing opportunities for positive charges. Be careful though to watch out for some tricks. So we need to watch out for what's called cross conjugation. So what I want to do is consider a positive charge at some various points in interesting molecules. So cross conjugation means not part of a conjugated system. And it's really the conjugated system. That is, it assumes that our molecule has some sort of opportunities for conjugation or delocalization, but the positive charge isn't part of that conjugation. We looked at an example like this. This is a good example because the lone pair, or excuse me, the double bond can migrate to give rise to resonance structures that delocalize the positive charge. But what if we consider a cross-conjugated case where the positive charge was now at this carbon? You can't really do this. And in fact, you get to a weird geometry because this is actually sp hybridized. Before we had a hydrogen at that position, and we're taking it away, but not through a deprotonation event, probably through some sort of oxidation event. And that actually gives rise to a structure that's sp hybridized at that positive charge. And now we're linear. Whoa, things have really changed now. Okay. And then awful, I mean, great reaction if you can actually make it happen, but an awful intermediate to consider under normal circumstances is one where you put a positive charge on the on a benzene ring. So when you do this, this is actually not conjugate. You can't draw a resonance structure to neutralize it. Even if you dump the electrons from the bond into the atom, as close as you can get, you have a carbene where you draw a plus and a minus charge. In reality, this molecule has a lot of positive character. It's still electron deficient, and it's next to a positive charge on the molecule. That one down is in conjugation. So you can't put this directly on a benzene. So this is bad, both here and here. We say we're cross-conjugated. We're not part of the conjugated network. We can't draw efficient resonance structures that delocalize this positive charge. All we have to do is sort of move our atoms or install some additional atoms where we have positive charge present. Like this is a benzylic cation, and despite being technically primary, it's actually quite stable because the positive charge now is in conjugation. It's not cross-conjugated, so we can actually delocalize that. We can show some resonance structures if we need to indicate to us that positive charge can in fact exist inside the ring. It's great not to break resonance, or excuse me, aromaticity, which we've done here, but and then the other thing about this, if we look at this structure, we're again sp hybridized. So what does that mean for this geometry? Are we like near linearity? So 1, 2, 3, 4, 5, 6. Okay, so then we have a structure like this where we've got 180-degree bond angles. I know some benzene researchers in the crowd are saying, no, not 180, but still not a good bond angle. Okay, not anywhere near the 120 that we need. Okay. But there are other rings that we can see positive charges existing in, and that is just a few aromatic rings. Let's just write it this way. So positive charges in aromatic rings Well, I'll show you one where the positive charge is actually part of the aromatic ring, and that's a 7-membered ring. So we have a positive charge here, and this could be distributed across the entire ring. It is aromatic because it follows Huckel's rule, 4n plus 2. Here we have 6 electrons, same as benzene. That's how I remember. Now in this other example, I believe I'm just running out of gas enough to forget this name for sure, but I believe this is a pyrrolium. I'm gonna have to look that up. Pyrrolium. So it looks like benzene, but it's got a positively charged oxygen, and the positive charge enables us to use the lone pairs, one of the lone pairs in the oxygen to form the third pi bond of this system, and so it is aromatic. So pyrrolium. Sorry, super professional Googling this. So I thought, okay, so it's got some wicked spelling. But yeah, so this is a pyrrolium. Okay, and then I believe I know what this is. Yeah, got it. Even got the spelling. So this is tropylium and pyrrolium. So these are other aromatic molecules. They have positive charges built into the aromatic ring. Okay, I had to just look those up to make sure I knew what we were looking at. Okay, so that'll do it for this lecture. In the next lecture, we'll use this knowledge of stable positive charges to start to discuss aromatic, or excuse me, cationic rearrangements. Okay, so we'll see you next time.